Here we are now just about in the middle of chapter 6, looking at those chemical reactions and quantities. Hopefully you've had a little time to practice with the mole concept and get used to that relatively foreign concept for those non-chemists out there, but hopefully it's becoming second nature and we're turning you all into chemists throughout the course of the semester. Our last lecture topic here in Chapter 6 was the mole, and hopefully that's become more familiar to you and you're getting better at using the mole and interconverting between the mole and Avogadro's number, because now we're going to extend it one further to talk about what's known as molar mass. And again, anything based on that mole is going to be pretty important for the remainder of the semester and for Chem 142 as well, or whatever course you follow up in that's heavily chemistry based. So let's make sure that we get this molar mass concept down the first time through and practice it as we need to until you're comfortable. If we define molar mass, the molar mass is the mass of 1 mole of a substance. So it's not that hard at all, right? It's pretty self-explanatory, at least the term molar mass. If we want to know exactly what that is, it's the number of grams that equals the atomic mass of that element. So it's really nice, those numbers that we have in our periodic table, we've always talked about as sort of the mass of a single atom of the substance in atomic mass units. Well, now we can talk about the mass of a mole of the substance in grams. What you've probably noticed is it's rounded to the tenths place for use in our text, although certain elements we tend to know more thoroughly, like carbon and sulfur here we have to the hundredths place. We tend to round to the tenths place here for the problem solving that we'll do. Let's follow up with a learning check right off. We don't want anyone to get lost already in the chapter. So let's make sure that you understand the importance of what we just went through there with the molar mass. So for this learning check, if you would provide the molar mass of the following elements to the nearest 0.1 grams, potassium, tin, and silicon. Pause the video now, consult your text or that document on Blackboard. That's the file for use on the exams. That's just the bare bones periodic table, and go ahead and report these values for these 3 elements. Pause the video here, start back up when you're ready. So hopefully you arrived at 39.1 grams for the molar mass of potassium, 118.7 grams for the molar mass of tin, and 28.1 grams for the molar mass of silicon. Depending on the table you consulted, you might have been able to go further than the tenths place, but again, for the problems that will work and for the purposes of this course, we'll use the nearest tenth of a gram as our final value. So it probably wasn't too challenging to find the molar mass of an element. It's the same process, whether we're talking about a really light element like hydrogen or a really heavy element like lead. It's the same basic process of finding the value on the table and reporting it to the nearest tenth of a gram. To find the molar mass of a compound gets a little more complicated. So here's our guide for calculating molar mass. First, we need to obtain the molar mass of each element in the compound. Secondly, we'll multiply each molar mass by the number of moles, the subscript in that formula for the compound. And finally, we'll calculate the molar mass by adding up the masses due to each of the elements present in the compound. Again, our guideline is to use the nearest tenth of a gram, but I forget that as much as you will. So you may end up with values that are just slightly off from the values that you'll see here, and that's okay. If there were an exam question, for instance, and you were close but not exactly right on any of the answer choices, you would go with the closest. I wouldn't have the answer choices so close that you'd be penalized for not going to the nearest tenth. And if you had gone further out, for instance, you would still get this, your answer would be closest to the correct answer. All right, so for our first compound that will work together, let's figure out the molar mass of calcium chloride. So we'd calculate the mass of calcium chloride to the nearest 0.1 grams using our application of our process, right? First, we're going to analyze the problem for what's given and needed. We're given the formula unit, CaCl2, and we need to find the molar mass of calcium chloride ultimately, but that means we're going to have to know the molar mass of both calcium and chlorine as elements. So step 1 involves obtaining those molar masses for each element, and at least to the tenth of a gram, we have 40.1 grams for a mole of calcium and 35.5 grams for chlorine. Again, if you look at the table, it's probably 35.45. So rounding up, we may end up with slight differences if you take it to the 35.45 versus rounding to the 35.5, or if I forget to do it and I do it the other way. So we may end up with slight differences, but rest assured, if you do it the right way, your answer will come up closest to the correct answer. Moving on now to step 2, we'll multiply each molar mass by the number of moles, the subscript in the formula. So for calcium chloride, there's just 1 mole of calcium and 1 mole of calcium chloride, so we'll multiply through by 1. All that really does is cancel the unit of moles of calcium and gives us grams of calcium now. For the chlorine, there's 2 moles of chloride and 1 mole of calcium chloride, so we do have to multiply that value by 2, and we end up with 71, technically 71.0 grams of Cl for our mass due to chlorine, or chloride ion in this particular ionic substance. Finally, when we sum the masses together, the 40.1 grams of calcium plus the 71.0 grams of chlorine as chloride ion gives rise to a molar mass for calcium chloride of 111.1 grams of calcium chloride per 1 mole of calcium chloride. Notice we don't treat ions any differently than atoms. Those electrons that are gained or lost are so insignificant in mass compared with the mass of the atom that we can use the neutral atoms from the periodic table even when dealing with ionic substances like calcium chloride. Now that we've worked an example together, let's follow up with a learning check. And in this learning check, you are going to determine the molar mass of potassium phosphate to the nearest 0.1 gram. So apply those same principles that we just used. Now you've got a third element to worry about. So just take care to do the molar mass for the contribution of each of these elements in the correct quantity, sum them up at the end, and when you're ready, after you pause the video now to do your work, start it back up and we'll see how you did. So here in the first step, we're going to obtain the molar mass of each element. So just looking on the periodic table and correcting them to be to the nearest tenth of a gram, we have 39.1 grams for potassium in 1 mole of potassium, 31.0 grams of phosphorus per 1 mole of phosphorus, and 16.0 grams of oxygen per 1 mole of oxygen. Here in step 2, we'll multiply each of those molar masses by the number of moles, the subscript from our formula. So for potassium, we had 3 moles of potassium in potassium phosphate. We had 1 mole of phosphorus and 4 moles of oxygen. So now we have the mass due to each of those 3 substances, and we're ready for our final step. All right, so here in step 3, we'll calculate the molar mass by adding the masses of the individual elements involved. And when we sum those masses correctly, we should arrive at a molar mass of potassium phosphate of 212.3 grams of potassium phosphate per 1 mole of potassium phosphate. So hopefully that worked out well for you. It's a very important skill. It's something that is actually so important. Let's do another learning check to make sure we're getting it. Okay, so this time your learning check asks you to find the molar mass of Prozac. Prozac C17H18F3NO is an antidepressant that inhibits the uptake of serotonin by the brain. What is the molar mass of Prozac? So go ahead, calculate it correctly. Don't just guess here. It is a multiple choice question like your exam questions, but please do follow that process and figure out the exact value and then identify which of the answer choices A, B, or C is correct. Pause the video here. When you're ready, start it back up and we'll see if you were correct. So our first step, of course, is to analyze the problem. We're given the molecular formula for Prozac, and we need the molar mass of each of the atoms present, and then for the total compound. So here we go. We've got a lot of different atoms present, right? 5 this time, which is the most we've done so far. So obtain the molar mass of each of those elements from the periodic table, rounded to the nearest tenth of a gram, and here they are. Hopefully that's what you found as well. Now on to step 2, we'll multiply each of those molar mass values by the number of moles from the subscript in the formula. So we find the total grams of carbon in 1 mole of Prozac to be 204.0 grams, the 17 moles of carbon times 12.0 grams of carbon per mole. And then we do likewise for the remaining substances to get the overall molar mass due to each of the elements present. Finally here, moving on to step 3, where we sum each of these values, we end up with a total molar mass of Prozac to be 309 grams, technically 309.0 grams. Each of them were to the nearest 10th place were resulting in a 0, so we would have 309 or 309.0 grams. But based on our answer choices, we really only had 309 as a possibility, and I believe that was choice C if you answered it correctly. Here's a nice visual to show the difference between the grams and the mole amount. So each of these substances pictured is 1 mole of the substance. So if it's sulfur, it's 32.1 grams. Iron there is almost twice as much on a gram basis, but because it's so dense, it looks like even less than the relatively less dense sulfur. Sodium chloride looks sort of in between, although its mass is greater than either. And then when we go on to potassium dichromate or sucrose, table sugar there, C12H22O11, we see that we have increasingly higher masses, and at least after sodium chloride, increasingly visible volumes of these substances. But again, they all contain 1 mole of that formula unit, whether it's the element itself or whether it's a formula unit in the case of an ionic substance like sodium chloride and potassium dichromate, or a molecular compound like sucrose. All of these represent 1 mole of the substance of interest. So now that we've gotten a little better, I hope, at molar mass determination, let's consider using molar mass to generate conversion factors. So methane, CH4, also known as natural gas, is used in gas stoves and gas heaters, very common in our area here in the southern tier of New York. 1 mole of methane, CH4, equals 16.0 grams of methane, 12.0 grams from the carbon, and then 1.0 grams from each of the 4 hydrogens for that total of 16.0 grams. So we can use that molar mass relationship to get conversion factors either with the molar mass up top and the mole of methane in the denominator, or the inverse of that as we see here on the slide. As I hope you've become accustomed in the course, now that we have another type of conversion factor, we can now talk about calculations using that. And in this case, calculations using molar mass. We can calculate the moles or the grams of a substance from the grams or the moles of a substance. So first, whichever direction we're going, we need to state the given and needed quantities. Then we'll follow up with a plan to convert grams to moles or moles to grams, depending on which direction we're headed. Third, we'll determine the molar mass and write conversion factors. And then finally, in our last step, we'll set up the problem to convert moles to grams or grams to moles, depending. So here we have an example converting mass to moles for potassium chloride. Our question is, how many moles are present in a 65.1 gram sample of potassium chloride? So step 1, state the given and needed quantities. To analyze that problem, we find that we're given 65.1 grams of KCl. What we're really looking for is the moles of KCl that represents. Step 2, we'll develop our written plan to convert from grams to moles. So grams of KCl, we'll use the molar mass as a conversion factor to end up with moles of KCl. Now moving on to step 3, we'll determine the molar mass and write conversion factors. So 1 mole of KCl equals 74.6 grams of KCl. That's not a magic number. The way I got that number is hopefully the same way you did. I took potassium at 39.1 grams per mole plus chlorine at 35.45, which we rounded to 30 5.5 grams, and when we add the 35.5 grams from chlorine plus the 39.1 grams from potassium, we end up with an overall mass of 1 mole of KCl to be 74.6 grams. We can have the conversion factor with either the mole of KCl in the numerator and the gram mass of that mole in the denominator, or the inverse. Finally, step 4, set up the problem to convert grams to moles. This is where we have to decide which form of the conversion factor we use, and if we want to cancel grams of KCl, obviously we will need the grams of KCl in the denominator and the mole of KCl in the numerator for our conversion factor to give a total of 0.873 moles of KCl. Looks right. We know that it's less than 1 mole because 65.1 grams is clearly less than 74.6 grams, and so we can do that logical check to make sure that we did the calculation correctly, at least had the form of that conversion factor correct instead of getting its inverse. Now that we've worked that together, it's your turn to work a learning check on your own. The learning check that you'll look at concerns acetic acid C2H4O2, which gives us the sour taste to vinegar. Calculate the moles of acetic acid present in a 25.8 gram sample of acetic acid. So go ahead, apply those steps, do your best to work this on your own. When you're done or when you're stuck, go ahead and start back up, and hopefully you are able to successfully complete the question and end up with the same answer that we will together once you start the video back up. All right, so in the first step, we'll state the given and needed quantities, and we'll analyze our problem here to find that we have been given 25.8 grams of acetic acid. We need the moles of acetic acid. Step 2, write our plan to convert grams to moles. Well, we're going to use that molar mass to convert grams of acetic acid into moles of acetic acid. Moving on to step 3, we'll determine the molar mass and write conversion factors. So 1 mole of acetic acid, C2H4O2, gives 60.0 grams of acetic acid, 12.0 grams for the carbon, and we have 2 of those to give 24.0 grams of carbon, plus 4 times 1.0 gives us 4.0 grams of hydrogen, plus 16.0 times 2 gives us 32.0 grams of oxygen, and when we sum those values, we arrive at 60.0 grams total. So we can either say 1 mole of acetic acid over 60.0 grams for our conversion factor, or 60.0 grams of acetic acid over 1 mole of acetic acid for our conversion factor. Finally, here in step 4, we're going to decide which form of the conversion factor to use, and then solve it for the actual numerical value here for moles of acetic acid. So in this example, we have 25.8 grams of acetic acid. Obviously, if we want grams of acetic acid to cancel, we'll need to multiply by the form of the conversion factor, 1 mole of acetic acid divided by 60.0 grams of acetic acid. When we calculate that correctly, we should arrive at a value of 0.430 moles of acetic acid. So hopefully you were able to get that on your own. If not, and hopefully it makes sense now, if it's still causing you trouble, please do try some additional problems on this concept, and certainly reach out to me if necessary. Here's a nice graphic to show the connections between mass, moles, and particles. I know many of us are graphical thinkers, and to have a graphic organizer like this may be useful. So if you have the grams of an element, you can use the molar mass to convert to find the moles of that element, and then also you can convert from moles to atoms using Avogadro's number, or ions if we're dealing with a charged species. From atoms, we can convert into molecules or formula units using those subscripts. From molecules or formula units, we can use Avogadro's number to get to moles of the compound. And finally, once we have moles of compound, we can interconvert between grams of compound and moles of compound by use of the molar mass. So we've got a lot now that we can do from these seemingly distinct ideas. We can combine them in new and fascinating ways, and pretty soon we'll be combining them with the idea of following a chemical reaction, which was the whole thrust of Chapter 6 here, was chemical reactions. So we can even talk about moles of a given reactant and relate that to moles of another reactant or moles of a product. And we're really getting to the point where we know an awful lot, believe it or not, and we can do some pretty powerful chemistry. But before we head into the lab and start making new and wonderful things, let's pause now for a learning check. Let's make sure we've got these core concepts squared away before we start to complicate life any further. So in this learning check, calcium carbonate, CaCO3, is found in antacid tablets. If we have a 3.20 mole sample of calcium carbonate, how many grams are present? So go ahead and pause the video here and apply those steps that we've practiced to determine the number of grams of calcium carbonate present in a sample that is 0.320 moles of calcium carbonate. All right, so starting off, as we always do, by stating the given and needed quantities and analyzing our problem to find that we have 0.320 moles of calcium carbonate given, and we need the grams of calcium carbonate that quantity represents. Step number 2, we need to write a plan to convert grams to moles, or in this case, moles to grams, and the way we'll do that is by using molar mass. So we'll take the moles of calcium carbonate, use the molar mass value for calcium carbonate to determine the grams of calcium carbonate. Step 3 here involves determining the molar mass and writing conversion factors. So the molar mass isn't given, but just by having the formula for calcium carbonate, or really even just the name, now that we have naming conventions down and we've gotten to know those polyatomic ions, I hope by now, that carbonate, for instance, is CO3 2-, you'd know that you would need 1 Ca2+ to charge balance. So we know an awful lot, and we can find a lot of information from a problem setup. And so this time what we found is the molar mass. 1 mole of calcium carbonate has 1 mole of calcium, 1 mole of carbon, and 3 moles of oxygen. And when we find those values based on the molar mass of each of those substances in that given quantity, we should sum to get 100.1 grams for a formula unit of calcium carbonate. And now the question becomes, do we use the 100.1 grams of calcium carbonate over 1 mole form, or do we use the 1 mole over the 100.1 rather grams of calcium carbonate? So hopefully you've already determined which is correct for this question. And here we see it was the 100.1 grams of calcium carbonate over 1 mole of calcium carbonate that was the correct conversion factor, so that we can cancel moles of calcium carbonate and arrive at 32.0 grams of calcium carbonate for our final answer. 0.320 moles of calcium carbonate was given, and therefore 3 sig figs in our starting value gives rise to 3 sig figs, 32.0 grams of calcium carbonate in our final answer. So hopefully the idea of molar mass and using molar mass as a conversion factor has become more comfortable through this lecture. If not, please do continue to practice and certainly reach out to me if I can be of any help. But hopefully it's all starting to come together and you'll be eager to join me in the next lecture for this chapter.